All right, so welcome back to chapter 6. And so the question that I left you with was, how do we know what climate was like before written records? So paleoclimatologists are the ones that study and reconstruct this. And various materials give us various lenses. For instance, tree rings can take us back a couple thousand years, and they can show us a climate on a year-by-year basis. Corals and glaciers can also do this. We can look at cave deposits, which go back decades. So the bottom of caves, the mud that builds up, right? Same thing at the bottom of lakes and the bottom of oceans. And the bottom of oceans can go back millions of years, right? Uh, One thing to notice is the further back we go, the resolution gets a little more blurry, if you will. So, for instance, with a tree ring, if the tree is 1,000 years old, and that's not too uncommon, right? Every year the tree grows, the ring is thicker or thinner depending on how the weather was like. So we can see every year a good indication of, say, moisture or rainfall, right? Corals grow the same way. With glaciers, we can look at things that happen with the snow, how much snow falls. We can actually look at the chemical content of the snow and see various things like pollen debris, uh, seeds in the air, that kind of a thing. And then with lake sediments, marine sediments, we're looking at actually what's in the mud. So like certain types of single-celled organisms leave behind traces that detail what the climate must have been like. For instance, if you're looking at pollen samples and you find a glacier from, say, 8,000 years ago, you can actually look at the pollen or that's in the air that was trapped in that ice. And if there's a lot of pollen from plants that grow in warmer climates, that means then there was a warmer climate, that kind of a thing. So if you look at here some images, right, these are actually sediment coils. This ship here can go out in the middle of the water, ocean, and drill deep down and take a sample, a tube, and they can actually look at these. And layers, right, the deeper down in the sediment, the further back in time. And the same thing with glaciers. Glaciers are actually built layer by layer over thousands of years. So, now that we know how we can figure this out, let's talk about the next big connection, which is carbon. So you've probably all heard talk about, we need to reduce our CO2, carbon dioxide. And carbon is the main thing we're going to focus on. Carbon is a very common element. It's in more things than just the air. All living cells have carbon in them. That's why it's called carbon-based life. It actually bonds with many other atoms to make really unique and long chemical chains. So anything that is alive has carbon. Rocks have carbon. There's carbon in the air. There's carbon in water. Um, right? But there's this idea of carbon cycles. How does carbon move through the different spheres of Earth, the biosphere, the lithosphere, for instance? And the long-term cycle, carbon is stored in the lithosphere, in the ground. And 99% of the carbon that is on Earth is actually stored in this long-term storage. And this is stored for millions of years, right? Carbon is removed from the air and from the water through weathering and erosion, eventually is buried as sediments and turned into rocks, or the burial of plants and trees that use carbon. The plants breathe in carbon dioxide. They grow. When they die, they're buried. They're turned into coal or oil, and they're preserved. Okay. In fact, fossil fuels like natural gas and oil are the remains of carbon organisms of plants. So carbon leaves the lithosphere through two ways: through volcanic eruptions that remove it from the lithosphere, or from humans digging it up as fossil fuels and burning it. So here's an example: carbon in the air, right, combines with water in the clouds to make carbonic acid, rainwater, which is then washed down into the ocean. The carbon atoms, the carbon atoms, bond with calcium, and they're used to form limestone or make shells for animals. Then eventually they fall to the bottom of the ocean as sediment, where they're buried for millions of years. Another thing that happens is that carbonic acid that falls as rain will weather rocks and pull carbon out of the rocks as well and remove it right down here through chemical weathering. Okay, so all of this works to basically pull carbon from the atmosphere and from the water and turn it into bicarbonate, which is basically seashells, which is then buried at the bottom of the ocean. Now, how does it get back? Well, This stuff in the bottom of the ocean, these rocks can eventually be turned into other rocks that maybe get near a volcano, and when a volcano erupts, any carbon that is in the rocks is melted, and then the gas is released. And so volcanoes every year dump a ton, actually 130 million tons of carbon. Okay, so that's the long-term process, the carbon cycle. There's also a short-term carbon cycle. And here we're moving basically through the atmosphere to the biosphere and the oceans. The oceans, ocean water can absorb carbon. Carbonated water, by the way, is the same thing as soda. So water can absorb a small amount of carbon. And there's actually a lot of carbon dissolved in the oceans. There's a lot of it right there. It's a relatively short holding time because it can be released back into the atmosphere or absorbed by other plants. Also, trees, plants can absorb the carbon when they breathe. And then when the plants die and they rot, the carbon can be released back into the atmosphere. So this happens in a much shorter term than the millions of years of the long-term cycle. Now, one of the things we have noticed is that the long-term carbon storage takes millions of years. We as humans have greatly made that faster, mainly by digging that carbon up. Coal and oil are mainly made of carbon. And so we dig up coal, we dig up oil, we dig up natural gas, and we take those materials that have carbon in them that would have been stored for billions of years, and we burn them for fuel. And in doing so, right, we release that carbon back into the atmosphere. So we're basically speeding up the long-term cycle. We're also speeding up the short-term cycle by deforestation, by burning down the forests. The carbon that is stored in those trees is released when we burn them. So you can see that fossil fuel burning releases about 31.6 billion metric tons and 3.5 billion tons just from burning the forest. So that's a really sizable chunk of carbon that we are adding to the atmosphere. Which leads us to the next aspect, the anthropogenic greenhouse effect. So we know that the atmospheric CO2 is rising. It's rising to 400 parts per million, and this is primarily through human activities. Volcanoes are not erupting at a faster rate. What is increasing is the amount of oil and coal and natural gas that we are burning, and the amount of forests that are being burned down. So currently, CO2 is going up at about 2.5 parts per million a year, and this is seeing temperatures rise. It's basically fostering the greenhouse effect. In fact, I checked this yesterday, so I've got to double check this. The current ppm measurement is 417.19 at the observatory in Mauna Loa, Hawaii, which is where we do most of our monitoring. Let's take that back. So, beginning in 1958, a scientist named Keeling actually started monitoring in Hawaii at the observatory the CO2 change. Okay, so we actually have direct records since 1958. We do know that before 1800, CO2 concentrations were much lower, and that they began to rise. We also see, looking at the various records, that whenever carbon in the atmosphere rises, so does temperature. When it drops, so does temperature. They kind of go together. They follow. Temperature, carbon. Okay? So, using that logic, right, up until recently, in the last, say, roughly 800,000 years, temperatures have been somewhat cooler. Carbon has never been higher than 300, and now we're currently a little over 400. So this is the observatory in Hawaii. It's on top of the tallest volcano, so it's about 14,000 feet up. They take air samples, and he started measuring in 1958 the amount of carbon. And you'll notice that it goes up, 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 up. It actually goes up in the winter, down in the summer. Up in the winter, down in the summer. So that was the first question. Why is it changing like that? And the thought was, well, in the winter, people have to burn more oil or more fuel to stay warm. But the general trend is year over year an increase. And not only that, the rate of increase has been getting faster. So in the 60s, carbon was increasing at a rate of a little under 1 part per million a year, whereas today we are increasing at a little over 2 to 2.5 parts per year. So not only is the amount going up, but you'll notice this curve is beginning to even go even higher. Now, how do we know what carbon was like before this? Because I just said that carbon has never been higher in the last so many thousand years. But we only have direct records. We weren't taking samples before the 1950s. Well, if we go to ice cores, here in Greenland, Greenland's covered with 2.5 miles of ice, which is about I think 800,000 years old approximately. We can drill down, and in the ice, the deeper you go, the older it is, there's actually air bubbles from each year the ice was made. These are tiny little air pockets, so we can basically sample what the air was like when this ice was created. And going back, see, here's our direct records until the 50s. We can see the amount of carbon, and this is only going back 1,000 years, and it's pretty steady. And then right about 1800 it begins to go up, and then really up. So this is the pattern that we see. When we look back at other ways, and we look back at carbon in the atmosphere in the last 800,000 years, it's fluctuated. Look at temperatures. That's almost a direct relationship. You could literally lie those line on line and really see almost no difference. So this leads to what we call the anthropogenic greenhouse effect. Remember, there is a natural greenhouse effect, but what this says is that the addition of CO2 caused by people, the man-made addition, and other gases we'll talk about, is accelerating the greenhouse effect, right? It's making it worse. So we are, in a sense, forcing climate that way. Additionally, the ice albedo feedback that we talked about in the Arctic is warming it twice as fast. So areas in the north, in northern Canada, the North Pole area, the ice and the snow are melting even faster. And once that ice and snow melts, the ground gets warmer every summer, which melts more ice and snow. The warmer it is, the less ice and snow falls. So the next summer, it gets even warmer. And the less ice and snow falls, and the next summer even warmer. And so we're kind of starting to see this effect. The areas at the poles, especially the Arctic, are warming twice as fast as the rest of the world. So when we look at that, right, and this is just temperature anomalies, you look at the average, this red solid line here is the 5-year average. This is the average of every year. But when you smooth it out and see the general trend, you can see that since the 1890s, it's been gradually getting warmer, but really more so in the last, say, 50 or 60 years. And this map shows Arctic warming. What this shows is average temperatures in December from 2003 to 2013, so over a 10-year period. And the darker the red, the warmer than average. So this would be right here. This white would be no change. And very few areas of the world had no change. Anything that is orange or red has seen temperatures higher than average. And only a few areas have seen temperatures lower. Very few. But the biggest departure from average has been the Arctic. So we're going to pause right here, and we'll come back with some more climate change data in the next part.